Hi, in this video we're going to be doing the Unit 13 problem set, which will essentially be our study guide for our solution equilibrium unit. So first it says the pH of solution is 0.05 molar HF and 0.05 NaF. So NaF will be a common ion. So HF plus H2O will form F minus plus H3O plus, because Na is a spectral ion since it's a weak conjugate acid. Alright, now over here, let's use the right chart because we do not need to use the Rebecca chart to show the consumption of moles. And over here we have 0.05, and over here we have 0.05 as well. So let's cross out water and put 0 over here. This will be minus x, 0.05 minus x, this will be plus x, 0.05 plus x, this will be plus x, and this will be x. So what's a Ka? Because we're producing H3O plus, we're going to be using Ka. What is a Ka for HF? HF is 7.2 times 10 to the negative fourth. 7.2 times 10 to the negative fourth power is equal to x times 0.05 plus x divided by 0.05 minus x. Because our x is so small, these two will cancel each other, and the 0.05 and 0.05 will cancel each other. So x is equal to 7.2 times 10 to the negative fourth. So all of these cancel out with each other. Now that we have x, we can use pH is equal to the negative log of x, which is our concentration of H3O plus, and now we use negative log of 7.2 e to the negative fourth power will give us 3.142, which runs to 3.14 pH. Now that will be our answer choice A. So next, what is the pH of solution, which is 0.01 molar in HA and NaA? So this is the same type of question as above. So we have HA, and I told you the Ka, so great. So HA plus H2O will form 8 minus plus H3O plus, and we just do the same process as above. So this will, we'll use the right chart, and this time it's 0.01, and A minus is 0.002. 0.002. So it'll be minus x, 0.01 minus x, it'll be plus x, 0.002 plus x, it'll be plus x and x. So this will be Ka, which is 9.0 times 10 to the negative 6 power, which is equal to 0.002 plus x times x divided by 0.01 minus x. Now because our x is small, we can remove this and remove this. So 9.0 e to the negative 6 power times 0.01 divided by 0.002 will give us our x. And that equals 4.5 times 10 to the negative 5th power. If we take this is the concentration of H3O plus, so pH is going to be equal to the negative log of x, which is going to be equal to negative log of 4.5 e to the negative 5th, which is going to be equal to 4.35. So 4.35, that will be our answer choice A. Number 3, in 20 milliliters of 1.0 molar NaOH is added to this in NH3 and 0.5 molar of NH4NO3. Okay, so what would it be the pH change? So first let's show this solution. Alright, we have 0.4 NH3 and 0.5 molar NH4. So HNO3 is a strong acid, so this is a weak conjugate base, so this will be a spectral ion, will not be included. So NH3 plus H2O will form NH4 plus OH minus. Okay, now this is our reaction, and we have 0.4 and 0.5. This would be 0.4, this would be 0.5. Now if we do right chart, yeah. So this would be minus x, 0.4 minus x. This would be plus x, 0.5 plus x. This would be 0 plus x. This would be x. So because we're producing OH minus, we're going to use Kb. So first let's find the Ka for NH4. NH4 Ka is 5.6 times 10 to the negative 10th. Ka is equal to 5.6 times 10 to the negative 10th. Now if we do Kw divided by Ka, Kw divided by Ka, so 1.0 e to the negative 14th power divided by 5.6 e to the negative 10th power will give us 1.7, 1.79, 1.785, 1.786 rounded times 10 to the negative 5th power. Now that is KB, which will be equal to x times 0.5 plus x divided by 0.4 minus x. X is small, so we can remove this and remove this. So our previous answer, times 0.4 divided by 0.5 will be equal to x. X is equal to 1.43 times 10 to the negative 5th power. But that is OH. So this is the concentration of OH minus. So in order to find the pH, we're going to be using the equation pH is equal to 14 plus the log of x, which will be 14 plus the log of that, which will be 14 plus the log of that, which will be 9.1549. So 9.15 is our answer. That is initial concentration of 0.4 and 0.5 molar of NH3 and NH4+. Now, time to add a new substance into it. And this time we're adding NaOH. NaOH is a strong base, so Na plus is going to be a strong conjugate acid. No, NaOH is a strong base, so Na plus is going to be a weak conjugate acid. So we're going to remove Na, and we're only adding OH into it. So now we're going to use, because we're adding OH, we're going to be using this part of the equation, NH4 plus the OH part. Because when we add OH, this will only react with the NH4. So our reactants have to be NH4 plus OH minus. Now when you add these two together, it's going to form NH3 plus H2O. So this will be Rebecca chart because we need to show the consumption of the moles first. Now, because we're using a Rebecca chart, we need to find moles. So how many moles of OH minus is added? We have 20 milliliters of 1 molar solution. So 1 times 0.02 will give us 0.02. 0.02 molar. Concentration times their volume. Now NH4 and NH3, NH4 plus and NH3 are in the same solution of 200 milliliters. So we just need to multiply their corresponding molar. NH4, we have 500 molar. So 0.5 molar, 0.5 molar, not 500. 0.5 molar times 0.2 milliliter concentration. Milliliter is going to give us a mole of 0.1. And now for Na3 is 0.4 molar, so 0.4 times 0.2 will give us 0.08. Okay, now that's settled. We're going to subtract both sides by the smaller number, 0.02. 0.02 minus 0.02 is going to be 0, and 0.1 minus 0.02 is going to be 0.08. This is going to add 0.02, and it's going to be 0.10. So now, because we're adding a base, we're going to be using Ka this time. Actually, we don't even need to do that. Because they're now in the same solution, when we convert these back into molar, we're going to be dividing both by the same number, which means they can be cancelled out. Alright, when you divide both of these by the same number, the ratio is going to stay the same, so we can straight up use these numbers into our HH equation. Now to use the HH equation, we're going to be using POH because we're adding a base to an acid. So it's going to be POH, so it's going to be POH is equal to PKB plus the log of conjugate acid divided by the concentration of base. Now we can use moles because in the end it's going to be the same thing when you divide both of them by the same number, you divide each other. So let's see, POH is going to be equal to PKB. So what is KB? We found KB over here as 1.78 times 10, 1.786. So 1.786 e to the negative fifth, and we negative log that, it's going to give us 4.74, 4.75. So it will be 4.75 over here, 4.74, 4.75. Plus the log of concentration of the conjugate acid. Our conjugate acid is NH4, so it'll be 0.08 on top. And our base is our NH3, which is 0.1 on the bottom. So 4.75 plus the log of 0.08 divided by 0.1 is going to give us a POH of 4.74. 0.653. Now to find pH, we just subtract that from 14. So 14 minus that number will give us 9.35. And our NPH will be 9.35. And that will be closest to answer C, where we went from 9.15 to 9.35 after adding our 20 milliliters of 1.0 molar NaOH. Next, we have to calculate the pH of a solution prepared by adding 0.1 moles of HCl. Again, Cl is weak conjugate base, so we can delete it. Solution that is 0.1 molar HA in NaA. So Na, again, remove. So similar to the previous problem, we're first going to have HA plus H2O forming A minus plus H3O plus. I use a RBCA chart. This is going to be 0.01 molar at first. Cross this out. A minus is going to be 0.02, and this is going to be 0. Minus x, 0.01 minus x, plus x, 0.02 plus x, x. So Ka, let's see, will we be using Ka? Yes, because we're pretty H0 plus. So 9.0 times 10 to the negative 6 is equal to 0.02 plus x times x divided by 0.01 minus x. X is small. Our Ka is small, so we're going to remove this x and remove this x. Now 9.0 e to the negative 6 power times 0.01 divided by 0.02 will give you x equals 4.5 times 10 to the negative 6. X is a concentration of H0 plus, so negative log of x will give you pH of 5.35. So that is the initial. Now we're adding 0.001 moles of HCl, which is H0 plus, our acid, because H plus and H0 plus are the same thing. So now to show the consumption of the moles, we're going to use oh shoot, I wrote RBCA over here. This will be rice actually, because we're using minus x's. Now over here to show the consumption of the moles, this one we're going to use RBCA. So over here we use rice chart because our A minus is already part of this reaction. Now this, because this is going to form a new reaction, we need to use the RBCA chart to show the consumption of the moles first. So this is going to be, let's see, HCl is H2O plus. So when we're adding H2O plus, the only thing that you will be able to react with is A minus. You will not be able to react with HA. So our reactant side is going to be H3O plus plus A minus. Now this will form HA plus H2O. Alright, so we have 0.01 moles, and since we're using a Rebecca chart, so we're going to be converting everything to moles. A minus, we have 0.2. We have 0.02 moles. You have 0.02 molar in the beginning. So how many milliliters in that 0.02 molar? Let's see, it says 1 liter solution. So great, we can convert these straight to moles. So it's going to be 0.02 over here for HA, and A minus will be 0.01. Nope, just opposite. So for HA is going to be 0.01, A minus will be 0.02. Again, 0.01 and 0.02 multiplied by the 1 liter solution. So now this will be minus a smaller number, which is going to be 0.01. So this is going to be 0 over here, 0.01 over here, plus 0.01 is going to be 0.02 here. Okay, now we can use, because they're now in the same solution, we can use the HH equation. So because this time we're adding an acid to a base, we can use the normal one where pH is equal to pKa plus the log of conjugate base on top divided by acid on bottom. So pH is going to be equal to pKa. Ka is 9.0 times 10 to the negative 6 power. So negative log of 9.0 e to the negative 6 power is going to give us 5.05 pKa plus the log of, on the top is conjugate base. Our conjugate base is A minus, which is 0.01, and our acid goes on the bottom, which is 0.02. 0.02. That will give us a negative number, negative 0.30. So now if we add that to 5.05, it will be 4.74. pH is going to be equal to 4.745. So 4.75 to round it to the correct number suffix. 4.75. Let's see which is our answer choice, which is closest to our answer choice B. Number 5. What is the mole ratio of sodium acetate to acetic acid to be used in preparing a buffer having a pH of 4.35? So let's see. Sodium acetate is going to be what's the molar ratio to sodium acetate to acetic acid to prepare a buffer? So let's see. CH3COOH plus H2O is going to form NaCH3COO minus plus H3O plus. This Na can be ignored because it is a spectral ion. Okay, now this is what we have, and let's see. Ka of this CH3 would be acetic acid. Acetic acid, which is 1.8 times 10 to the negative 5th power. Oh wait, one thing. So how do you know it's not CH3COO minus? How do you know it's not the opposite way? Plus H2O to form CH3COOH plus OH minus, right? How do you know which one of these reactions to use? Well, the answer is it told you the pH of 4.35. So this one produces an OH minus. If you add the water to the base, then it will be producing an OH minus. But if you add the water to the acid, it's going to produce H2O plus. A pH of 4.35 means the solution is acidic. So you have to produce H2O plus, which is why this reaction will be the incorrect one. Now, okay, back to over here, Ka is equal to this, and we're going to use the we're going to find pKa by taking the negative log of this. So pKa, which is negative log of 1.8 e to the negative 5th power, then it's 4.744, 4.74. Okay, now, pH, to produce H2O plus, we're going to use the pH formula. pH is equal to the pKa plus the log of conjugate base on top divided by acid on bottom. So acid on bottom, our acid is, okay, we don't need to worry about that so far. So 4.74 is equal to pKb, which is 4.74. No, Ka, 4.35. The pH is 4.35 and the pKa is 4.7. So 4.35 is equal to the 4.74 plus the log of conjugate base divided by acid. So 4.35 minus 4.74 give you negative 3.9. Negative 0.39 is equal to log of conjugate base over acid. Now if we take 10 to negative 0.39 power, that is going to give us 0.47. 0.407, which is 0.41. Now what is this equal to? Our conjugate base divided by acid is equal to 0.41. So that is our ratio. Now let's make sure we have the base, sodium acetate, which is the base, over the acid. So base over acid. So this will be our mole ratio. For every 0.41 moles of sodium acetate, we'll have 1 mole of acetic acid, because this is what happens when we divide these two together. So which of these answer choices shows 0.41? And our answer will be C. Alright, so for number 6, it's going to be pretty much the same thing as above, except this time we're doing HCO3 minus and H2CO3. So we can do H2CO3 plus H2O, forming HCO3 minus plus H3O plus. Ka for H2CO3, we're going to be using Ka1 because the other thing is HCO3 minus. So Ka1 is 4.3 times 10 to the negative 7th power. So Ka is equal to 4.3 times 10 to the negative 7th power. Now pKa will be equal to negative log of that. Negative log of 4.3 to the negative 7th will be 6.36, 6.366, 6.37. Now pH of 7.40 is equal to 6.37 plus the log of conjugate base divided by acid. So 7.40 minus 6.37 is equal to 1.03 is equal to log of conjugate base over acid. 10 to the 1.03th power is equal to 10.71. 10.72. And this will be equal to the conjugate base over acid. Now let's quickly label here. This is acid because this is donating a proton. This will be a base and this is the one being donated, so this is the one donating in the beginning, so this one will be conjugate base, this one will be the conjugate acid. Alright, so let's take a look at it. Conjugate base is our HCO3 minus, and our acid is H2CO3. Does this match what we're comparing with? HCO3 minus H2CO3. It does. So our conjugate base, which is HCO3, conjugate base divided by acid, which is our conjugate base, which is HCO3 minus, divided by our acid, which is H2CO3, and the ratio will be 10.72. Now 10.72 of Cb for every 1 of acid, and this closely matched to this. Now, say you wanted to use the other HC, the opposite reaction, HCO3 minus plus H2O, forming H2CO3 plus OH minus. Alright, say you wanted to use this equation, and in the end you'll get the same answer, because this is going to be the base, the conjugate, this is going to be the acid, this is going to be the conjugate base, conjugate acid, this would be the conjugate base. Now, over here, you're going to be looking for Kb, and then use a pKb, and then after that, use a POH is equal to the pKb plus the log of conjugate acid on top divided by base on bottom to get this value, and do the same process, and in the end, you're going to get a number. If you use the correct ratio, the ratio will be conjugate acid on top divided by base on bottom. Now be careful, what is the conjugate acid? The conjugate acid is H2CO3. So in the end you'll be getting a H2CO3 mole ratio to HCO3 minus if you use the OH method, right? If you use the second reaction with OH. Now you don't want that because you want the opposite. You want the opposite of which is HCO3 minus to the mole ratio. You want to convert to HCO3 minus to H2CO3. And now I did the math already, so if you use the conjugate base method, in the end you'll get the concentration of Ca to B will be 1 to 0.09. You can do the whole process to make sure your answer matches mine. So you have 1 to 0.19, but you want the opposite, right? You want the conjugate base to the acid. So you want to flip these two. Now to do that, you're going to divide 1 divided by 0.09 to find out how many times you need to multiply both of these numbers by. 1 divided by 0.09 is 11.11. So, well, this 0.09 is rounded. So if you don't round it, you'll get the same number as over here, 10.72. So let's just use the rounded one, and this is going to be, so for every 1 of this, there is 11 of this 0.09. So if you multiply both sides by 11, you'll end up getting 11 to 1, which is our correct ratio of Cb to A, aka our HCO3 minus to our concentration of H2CO3. Number 7, what pH results when these two are mixed when 150 milliliters of 0.1 molar NH3 is mixed with HCl? Alright, Cl is going to be crossed out because it is weak conjugate base. So we're going to have NH3 plus H3O plus, because H plus, our remaining H plus from here is the same thing as H3O plus. And now we're going to use the RBCA chart first. So this will be moles, 0.1 molar times 150 milliliters, 0.1 times 0.150, which is 0.015, 0.015, and our H2O plus, wait, let me figure this out, NH4 plus H2O. And our concentration of NH4 will be, let's see, 50 milliliters times 0.2 molar. So 50 milliliters, 0.05 times 0.2 will be 0.01. And I'm gonna write the formula onto the side real quick. So moles divided by milliliters is equal to molar. So molar times milliliters will give our moles, this is the formula we'll be using to find all of our moles. So now I have 0.015 and 0.01. 0 over here and plus x. No, we're using RBCA. So we're going to subtract both of these by a smaller number, which is 0.01. Then give you 0.005, it will be 0. So this is going to be add 0.01, add 0.01. So this is going to be 0.01 over here. And now we have Ka Now we're going to have this reaction. And because our substance with the Ka is on this side, we're going to be using Kb of NH3. So NH3, we're going to be using Kb, which is POH, is equal to the pKb plus the log of conjugate acid on top divided by base. So Ka of NH4 is 5.6 times 10 to the negative 10. So 1.0 e to the negative 14th divided by 5.6 e to the negative 10th power will give you POH is equal to 1.786 times 10 to the negative 5th power plus the log of Ca divided by Cb, which is conjugate acid is NH4, which is 0.01, divided by base, which is 0.005. Now, that number, the previous pKb we found, plus the log of 0.01 divided by 0.005 give us a POH. Oops, sorry, this is Kb, not pKb. So, my bad, negative log of that. The pKb is actually 4.75. Okay, now we add that to the log of 0.01 on top and 0.005 on bottom. And our POH will be equal to 5.04. 5.05. So we do 14 minus 5.05 because that is POH. 14 minus 5.05 will be 8.95. And that is the closest to our answer, C, of 8.96. Alright, last question on this page. Calculate the concentration of H3O plus by mixing this of CH3 with NaOH. Again, this Na will be cancelled. Let's make our work easier. So CH3COOH plus OH minus will be a reaction. So CH3COO minus plus H2O. Alright, cool. We have, let's see, because we're adding OH minus, this will be Rebecca chart. So let's see, 4.2 molar. 2 molar times volume is 0.02, 0.04 will be 0.08. So that is 0.08. And we have 20 milliliters of 1 molar. So 1 times 0.02 will give us 0.02. And now this is 0 over here. And this will be crossed out. So minus x, no, minus 0.02. Minus 0.02. This will be 0 and 0 will be 0.06. And plus 0.02, it will be 0.02 over here. Okay. Now to find the concentration of our H2O plus, we must use our remaining reactant and product to form another reaction, and this time via Rice chart. Alright, so let's convert everything back to mole. Let's convert everything back to moles first. Molar. So this, our total new liquid is now 0.06 because we have 40 plus 20. So 0.06 divided by 0.06. So this is going to be 1 molar divided by 0.06 is equal to 1 molar. And 0.02 divided by 0.06 is going to be 0.333 molar. So our new will be what reactions we have. So we have CH3COOH plus H2O. Our reactant remains a reactant, and this time it will produce CH3COO minus plus H3O plus. And now we plug the moles in. Alright, this will be 1 molar, and this will be 0.333 molar, and it will be 0 to start off with. Now subtract x, 1 minus x, now plus x, x, 0.333 plus x, and it will be x over here. Now we're going to be, because we're producing H2O plus, we're going to be using Ka of acetic acid, CH3COOH. Acetic acid is this one. And now this one is the same thing as CH3COOH. Alright, these two can be used interchangeably. They're both acetic acid. So this is going to be 1.8 times 10 to the negative 5th power. So K 1.8 times 10 to the negative 5th power is equal to x times 0.333 plus x divided by 1. 1 minus x. Because the x is so small, we can cross out these two x's. So the answer is going to be 1.8 e to the negative 5th power divided by 0.333 times 1, which we don't really count. And our answer will be 5x is equal to 5.41 times 10 to the negative 5th power. 5.41 times 10 to the negative 5th power is closest to A. So our answer choice will be A, and this is a concentration of H3O+. Now, what is the pH of solution made by mixing 0.1 mole of HCl and lithium acetate? Lithium acetate is LiC2H3O2. Now, LiOH is a strong base, so Li is a weak conjugate acid, so we can remove this. So we can remove the Li. And Cl is a weak conjugate base as well, so Cl can be removed. Okay, now we just have equation of C2H3O2 minus plus H3O plus, because H is the same thing as H3O plus. This will form HC2H3O2 plus H2O. Now first this will be Rebecca chart. We see, let's see, Rebecca, it gave us the moles. We have 0.1 mole of this, 0.1 mole, and 0.1 mole of HCl. So both of these are 0.1. Now if we minus both sides by 0.1, it's going to be 0 and 0. This is going to be 0 over here, and then plus 0.1, forming 0.1. Now this is going to be our new reaction because there's none of these left. So it's going to be rice chart this time. HC2H3O2 plus H2O will form C2H3O2 minus plus H3O plus. Now in that case, the initial will be 0.1, but this is a mole, so we convert to liter. Fortunately, we have a 1 liter solution, so it's going to be 0.1 mole over here. It'll be everything else is 0 minus x, 0.1 minus x. It'll be x plus x plus x, x, and x. So what is the Ka for C2H3O2? Acetic acid. So Ka will be 1.8 times 10 to the negative 5th, 1.8 times 10 to the negative 5th power is equal to x squared divided by 0.1 minus x. We can remove this minus x because K is small. So 1.8 e to the negative 5th power times 0.1, take the square root of that. It will give us an x value of 0.00134. Take the negative log of x. We're going to get our pH of 2.87. Let's see, 2.87, which is closest, which is B. Next, what is the mass of NaF will be? What mass of NaF will be added to 2 liters of 0.1 molar HF to yield a pH of 4.0? Alright, first let's see. pH. Alright, let's write the equation. Alright, HF plus H2O to form F minus plus H3O plus. This will be F minus. So this will be in order to do this, we're going to be using the pH equation. HH equation. pH equal pKa plus the log of ratio of, let's see, this will be conjugate base divided by acid. So first, what is the pKa? Well, the K for HF will be HF 7.2 times 10 to the negative 5th power. 7.2 times 10 to the negative 4th power, sorry, is equal to, oh, that is a Ka. So the pKa will be negative log of 7.2 e to the negative 4th power, 3.14. So pH, it told us, is 4.0. So we're given 4.0 pH, and this will be 4.00 is equal to 3.14 plus the log of HF, no, conjugate base, F minus over acid. So let's see, they're asking for the mass, so, and it told us the molar concentration for the HF. So let's use the molar concentration here, which is 0.1 molar. This will be X molar. So 4.00 minus 3.14 is equal to 0.86. 0.86 is equal to the log of the concentration of NaF divided by the concentration of HF, which is 0.1. So 10 to the 0.86 power is going to be 7.24. 7.24 is equal to x divided by 0.1. 7.24 times 0.1 will give you 0.724. 0.724. And that is molar moles over liter of NaF. Now, we want grams. So in order to do that, we're going to do, this is molar, right? We're going to multiply by our liter solution first. So we have 2 liters. So it'll be 2 liters. Let's just put a 1 down here. And after that, the liter will be gone and we have moles. So for every 1 mole of NaF, what is the weight? So what is the weight of NaF? Na is 22.99. F is 19. So when you add them together, it's going to be 41.99. So 0.724 times 2 liters, the liter and liter will cancel, and the moles and moles cancel after you multiply it again by 41.99. You will get a final answer of 60.80 grams of NaF. Okay, so 60.8 grams will be closest to 61 grams. Okay, here a 1.0 solution contains 2 moles of NH3 and 3 moles of NH4Cl. Cl will be removed because spectral ion, so let's remove this. And it shows a pH equal 9.07. If 100 milliliters of 6.0 molar were added to this solution, the pH would decrease by what? Alright, to show the consumption of moles, let's first create a Rebecca chart, RBCA. And then our equation will be NH3 plus our acid HCl, and the Cl will be spectral ion, so H plus will turn into H3O plus, H3O plus forming NH4 plus H2O. Now we're plugging in the moles because our Rebecca chart. 2 moles of NH3, 2, 3 moles of NH4, 3, and 0.6 molar times 0.1 mol, 6 molar times 0.1 liters will give you 0.6 moles. Now subtract both of these by 0.6, this will be 0 over here, and this will be 1.4. Now you add 0.6 to this, you get 3.6 over here. Now let's use this and form a rice chart. So this will be NH3 plus H2O, forming NH4 plus OH minus. We don't have to do all of this because we can use the HH equation. So we have OH minus, so this is the base, so we're going to use a POH formula. POH is equal to PKB plus the log of conjugate acid on top divided by base on the bottom. So POH is going to be equal to, let's see, what's KB? So KB is going to be 1.0 e to negative 14 divided by the Ka of NH4, which is 5.6 times 10 to negative 10, 5.6 e to negative 10 power. They give you 1.7, oh, sorry, that is the KB. KB is equal to 1.786. So we take a negative log of that, sorry, times 10 to the negative 5th power. Take a negative log of that, we're going to get 4.75. Plus the log of Ca on the top. Let's see, Ca is our NH4 plus, which is 3.6 on top. And then on the bottom will be our base, which will be 1.4 on the bottom. And that will be it, 4.75 plus the log of on top 3.6, on the bottom 1.4. I'm going to give you 5.16. Now if you do 14 minus 5.16, you're going to get 8.84. And that is our after pH. So when you ask how much the pH will decrease by, so we subtract 9.07, which is our original, minus our 8.84. Let's see what that gives us. 9.07 minus 8.84. We'll get a pH change of 0.23. Now 0.23 is our answer choice B. 2.0 liters of a hydrochloric acid solution with pH of 3.22 is mixed with 1 liter solution of NaOH with a pH of 10.7. The final 3.0 solution will have a pH of. So first, let's see. We have hydrochloric acid, HCl, which is a strong acid, and we also have NaOH, which is a strong base. So we have a strong base and a strong acid, except one of them is 2 liter and one of them is 1 liter. So first, let's convert all of these to Alright, let's convert all of these to concentrations of the corresponding H0 plus and OH minus. Alright, let's cross this OH minus out. So 10 to the negative pH's power 3.22 will give you the concentration of H0 plus, which will give you let's see, 10 to the negative 3.22's power is going to give you 6.026. Now 10 to the negative POH's power is going to give you a concentration of OH minus, and it told you the pH of the NaOH is 10.78. So 14 minus 10.78 is going to be equal to 3.22. So 10 to the negative 3.22 is the same thing as over here. So it's going to give us the same answer, 6.026. Oops, times 10 to the negative fourth. I forgot about that. Times 10 to the negative fourth. And this is a molar of HCl, and this is a molar of NaOH. I'm going to keep it OH minus over here and keep this as H0 plus. Now if we go here, set up rice chart, we'll have H3O plus, 2H0 plus because we have 2 liters, plus OH minus, forming 2H2O. Now this will no longer be 6.06 because that is for 1 moles of H2O plus. So if we're going to do this, we're going to have to do 6.026 e to the negative fourth power times 2 for the 2 moles. That'll give you 0.0012. And OH minus is going to be 1, so this is going to stay at 0.26 times 10 to the negative fourth power. When we divide both of these by a smaller number, which is 0.026 times 10 to the negative fourth power, it'll be 0, so 0.00112 minus that. And the answer will give us 6.026 times 10 to the negative fourth. And that is moles. Alright, because we used molar over here. So now that is moles, 6.026 times 10 to the negative fourth moles divided by our liters, which is a new solution of 3 liters. We'll get, let's see, that number divided by 3, we'll get 2.00, 2.001, 2.009 times 10 to the negative fourth power. Now with that, that is our concentration of H3O plus because we have no more OH minus left. So if that's the concentration of H3O plus, we can use negative log of this number, and the negative log of that number will give us 3.6697, which will be 3.70. 3.70 will be our answer C. Okay, here, what is the molarity of the original acetic acid solution? And instead we'll have 20 milliliters of acetic acid titrated with 0.05 molar of NaOH. And the K for that is this. Alright, so we can use, for this, we can use HA, which is our acetic acid, plus our NaOH, let's cross out the Na so we don't confuse ourselves, OH minus, will form A minus plus H2O, and this A over here is standing for acetic acid. This A minus will be acetic ion, the HA will be acetic acid. So if we use their equivalence point, we're going to be able to find what is original. So let's see, M1V1 is equal to M2V2. Alright, M1 acetic acid is going to be 20 milliliters of X, 20 milliliters times X volume, no, times the X molar, which will be equal to the second one, which is 0.05 molar, and it's going to be 0.05 molar times, let's see, what is the equivalence point? Alright, 60. So it's going to be 60 milliliters. Now with that, we're going to find our molar concentration of our first one. So 20 milliliters times, no, 0.05 molar times 60 milliliters divided by 20 milliliters is going to be equal to 0.15 molar. And that is our acetic acid solution for when it's original. Now, what is the acetic ion concentration at point A? The point A is when there is no NaOH added. So when there is no NaOH added, we're going to use HC2H3O2 plus H2O, forming C2H3O2 minus plus H3O plus. And simple rice chart will find us the pH. Oops, wrote it in the wrong place. HC2H3O2 plus OH minus, no, plus H2O will form us C2H3O2 minus plus H3O plus. This we need to write short for, and we know the original concentration from the previous problem, right? The previous problem says the concentration is 0.15, so this would be 0.15 over here, and then our concentration of, that's it, we don't have any OH. Alright, cool. So this would be 0 and 0 over here. This would be minus x. This would be 0.15 minus x. This would be plus x, x, plus x, x. So what is the K for acetic acid? It told us it's 1.8 times 10 to the negative 5th power. So it would be 1.8 times 10 to the negative 5th power is equal to x squared divided by 0.15. We can remove the minus x because the K is small. So 1.8 e to the negative 5th power times 0.15, take the square root of that. We're going to get answer of x. X is equal to 0.0016. And what does this X stand for? This X stands for the concentration of H3O plus and the concentration of C2H3O2 minus, which is our acetic ion concentration. So our acetic ion concentration, let's rewrite this, 1, 2, 3, this is 1.6 times 10 to the negative 3rd power, which is our answer choice A. Next, what is the pH of the solution at point B? So at point B, this time we're adding NaOH now. We have 30 milliliters of NaOH. So 30 milliliters times its concentration, our NaOH concentration, which is 0.05 molar. So 0.03 liters times 0.05 molar is going to give you 0.015. So we have 0.0015 moles of NaOH. Now let's grab the solution of, okay, we also got to find the moles of HC2H3O2. So we have 0.15 molar multiplied by 20 milliliters, 0.02, will give us 0.003 moles of HCl. Now we do Rebecca chart. The reaction is going to be, alright, not HCl, HC2H3O2. So it's going to be HC2H3O2 plus OH minus forming C2H3O2 minus plus H2O. So it'll be 0.03 over here, 0.003, it'll be 0.0015. Minus both sides by 0.0015, it'll be 0, and this will be 0.0015. And plus 0.0015, it'll be 0.0015. Boom, what do you have over here? Half equivalence point. So half equivalence point, the pH is going to be equal to pKb. So pH is going to be equal to pKa. And what is the K? The K is 1.8 times 10 to the negative 5th. So negative log of 1.8 e to the negative 5th power is going to be 4.74, equal to 4.744. And that is our pH, 4.74, which is answer choice B, because we're at half equivalence point. Alright, next, which point in the curve is the pH of the solution at 7.0? Alright, we're titrating, let's see, a weak acid with a strong base. So none of these points will be 7.0 because 7.0 will probably be around here. When we add more acid, the equivalence point is going to be higher than a pH of 7. So the answer will be E, none of these. If we're titrating a strong acid with a strong base or a strong base with a strong acid, then the equivalence point will be closest to extremely close to 7. At what point in the solution buffered? So for number E, anything past this line will be considered buffered. So remember, this this flat part is considered a buffer solution. So anything past this will be considered buffered, and our answer choice will be B. Anything past this line will be buffered. A 0.5 gram sample of monoprotic acid was dissolved in 10 milliliters of distilled water and then titrated. And the equivalence point for this titration occurs at pH of 8.94. Which of the following acid-base indicators will be suitable for the detection of the equivalence point? So the equivalence point, you want the pKa to be as close to the pH as possible. But over here, it didn't give us the pKa. Instead, it told us straight the pH range for it. So when it means this kind of question, just find whichever pH range contains 8.94. So which one of these, 8.94 is in which one of these value ranges, and it is D. It's in between 8.0 and 9.6. So our answer will be thymo blue. Next, given the following hypothetical acids, the pKa values are in parentheses. Which acid is the strongest? Again, lower pKa equal higher Ka equals stronger acid. So which of these has the lowest Ka? Well, the pKa. So the pKa values are in the parentheses, so it's 1.9, 10, 7, 9, and 11. Our weakest one will be A, HP minus. Over here it says the silver sulfate has KSP of 1.2 times 10 to the negative fifth at 25 degrees. What is the maximum concentration of Ag that can be obtained? Okay, so we're looking for the concentration of Ag by saturating water. Alright, so first let's write the salt. Ag2SO4 dissociates into 2Ag plus SO4 2 minus. Let's form a rise chart. This won't be existent because it's a solid. Over here we have 0 and 0. We plus 2s because of 2Ag, and we plus s, so 2s and s. And KSP is equal to Ag squared, Ag plus squared times SO4 2 minus. And then KSP is 1.2 times 10 to the negative fifth is equal to 2s squared times s, which is equal to 4s cubed. Alright, so 1.2 e to the negative fifth power, 1.2 e to the negative fifth power divided by 4, because 2s squared is 4x squared times s, so divided by 4, and then math 4 cube root of that is going to be equal to 0.0144. So 1.44 times 10 to the negative 1212 times 10 to the negative second power. But this only gives you 1s. But what do we have in Ag? In Ag we have 2s. So the answer choice is not A. We need to multiply this by 2, which will give you 0.0288. And that will be answer choice D. Next, the pH of iron 2 hydroxide is 9.40. What is the KSP of FeOH2? So to solve for this, it told you the pH, which you can convert to POH to find the concentration of OH minus, and then via using that, you can find the KSP. So let's see here. Our reaction will be FeOH2 forming Fe2 plus 2OH minus. This will be plus S, S, plus 2S, 2S. Now KSP is equal to the concentration of OH minus squared times the concentration of Fe. So let's use POH over here. Okay. POH is equal to 14 minus 9.49. 14 minus 9.4, 4.6. Now POH is 4.6, 10 to the negative 4.6 power. It's going to be 2.51 times 10 to the negative fifth power. That is our concentration of OH minus. So this is 2s. This is number of 2s. This number here is our 2s because this and this equal to each other. So now this is 2s. KSP is equal to OH minus squared, which is 2s squared, which will be equal to 2.51 times 10 to the negative fifth squared. Multiply that by 1s. What is the value of 2s? This is equal to 2s. So 1s will be 2.51 times 10 to the negative fifth divided by 2. So divide the previous answer by 2 will give you s equal 1.26 times 10 to the negative fifth. So over here we'll plug in 1.26 times 10 to the negative fifth. So our KSP will be equal to 2.51 e to the negative fifth power squared, which is our OH minus squared, times our Fe, which is 1.26 e to the negative fifth. And that will give you an answer of 7.94 times 10 to the negative 15th. 7.94 times 10 to the negative 15th is answer choice E. Number 18, what is the molar solubility of Ag2CO4? So I told you the KSP and told you the 10 molar solution in AgNO3. So first let's do a rise chart showing the dissociation of our salt, which will be Ag2CrO4 forming 2Ag plus CrO4 2 minus. This will be 0, 0 plus 2s plus 1s. So 2s over here and 1s over here. Next, now KSP is equal to AG plus squared times CRO for 2 minus. So this will be 2s squared times s, and the KSP is 9.0 times 10 to the negative 12. So we have 0.1 molar of AgNO3, and it asks us what is the molar solubility for AgCrO4. So we can use this 1.0 over here and plug it into our Ag. So it's going to be 0.1 instead of 2s, 0.1 squared. So 9.0 times 10 to the negative 12 is equal to 1.0 squared times s, and our s will be the molar solubility. So let's see, 9.0 e to the negative 12 divided by 0.1 squared is equal to 9.0 times 10 to the negative 10th. S is equal to 9.0 times 10 to the negative 10th, and that is our answer D. Next it says the KSP of XOH2 is 8.0 times 10 to the negative 12. What is the pH of a central solution of OH minus? Alright, so to find the pH, we're going to be using our concentration of OH minus, and then with that we can find the pH to find the pH. So XOH2, we don't know what X is, so it's going to form X2 plus plus 2 OH minus. Then we plus 2s, plus s, plus s, plus 2s, and to the form s and 2s. So 8.0 KSP times 10 to the negative 12th power is equal to s times 2s squared because we have 2 OH, which will be equal to 4s cubed. Now s will be equal to what? So 8.0 e to the negative 12 divided by 4, and then take the cube root of it, which will be 1.25, 1.26 times 10 to the negative 4th power. S is equal to 1.26 times 10 to the negative 4th power. Now, we need 2s to form the concentration of OH minus, so multiply this by 2. Multiply this by 2, so that will be 2.51. 2.52 times 10 to the negative 4th power, and we take the 14 plus the log of 2.52 times 10 to the negative 4th power will give us our pH, because that is concentration of OH minus. 14 plus the log of that number gives a pH of 10.40. So our answer is A. Number 20, the solubility of silver sulfide is 2.00 times 10 to the negative 5th at grams per milliliters. Calculate the KSP for silver sulfide. Alright, so for these kind of problems, you always start off with dissociation of the salt. So silver sulfide, Ag2S, so form 2Ag plus S2 minus. Then you form a rice chart. Cross this out, the initial is 0, 0 plus 2S plus S, 2S, S. Okay, next, the KSP. We're looking for the KSP. So KSP is equal to 2S squared times S. KSP is equal to 4S cubed, and the KSP, and then S is, what are we given? 2.00 times 10 to the negative 5th. Alright, first we need to convert this into concentration, which will be moles per liter. So 2.00 times 10 to the negative 5th grams per 1 liter. We're going to convert it to moles per liter. So 1 mole will have how many grams? So AgS2. So Ag will have, let's see, 107.87 times 2 plus 32.07 will give us 247.18. So 247, oh shoot, over here is 100 milliliters. Alright, so keep note of that. This will be 247.81 grams. Right now, grams and grams cancel out. We now have moles over 1,000 milliliters. So for every 1,000 milliliters, we have 1 liter. This way, the ml on the bottom and the ml on the top cancel each other out as well. So leave us with moles over liter. Now 2.00 e to the negative fifth power divided by 100 times 1 divided by 247.81 times 1000 divided by 1, which will be equal to 8.07 times 10 to the negative 7th moles per liter, aka molar. Now we have molar, we can plug into S, which is our concentration. So S will be equal to, our KSP will be equal to 4S, and S will be 8.07 times 10 to the negative 7th power cubed. So 4 times 8.07 e to the negative 7th power cubed will give you KSP of 2.10 times 10 to the negative 18th. 2.10 times 10 to the negative 18th is the closest to answer choice D. And again, over here, because we're using S, and S is part of the concentration, that's why we did all this to convert grams per 100 milliliters to moles per liter, and then we can plug it into S to solve for our KSP. Alright, now our last problem is titration problem, just like last unit's problem set, except this time we know how to use the HH equation, which should make everything faster. So let's see, we have HF and NaOH. So what's our initial when there's no NaOH? To be pure HF plus H2O, forming F minus plus H3O plus. We have a rice chart, and it told us we have 0.1 molar. Everything else is 0, 0, minus x, plus x, plus x, 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 0.1 minus x. What is the Ka for HF? Ka for HF, and we're going to be using Ka because of our H2O plus we're producing. So Ka, let's see, of HF is going to be 7.2 times 10 to the negative 4th power. 7.2 times 10 to the negative 4th power is equal to x squared divided by 0.1. We're going to assume the 5% rule holds, so we don't even care about the minus x over here. So 7.2 e to the negative 4th times 0.1 takes the square root of that. Then give you our x equals 0.0085. Negative log of x is going to be our pH, which is going to be 2.07. Next, calculate the pH after adding. Alright, now we need to first show RBCA, HF plus NaOH. The Na doesn't count, so it's just going to be pure OH minus to form F minus plus H2O. Initial is going to be moles. So 0.1 molar HF times 0.1 liters is going to be 0.01. And then NaOH, we have 0.2 molar. So 0.2 molar times 0.01 liter is going to be 0.02. 0.002 minus both sides by 0.002 plus 0.002 over here. It will be 0.002 over here, 0 over here. 0.01 minus 0.002 should be 0.008. 0.008. And now we're gonna do HH equation. So if we use this, we're gonna end up producing this reaction again, and then produce H3O plus. So the HH equation we're gonna use is pH equals pKa plus the log of conjugate base divided by acid. So conjugate base is F minus 0.2. So pKa, we found the Ka over here at 7.2 times 10 to the negative 4th. So negative log of 7.2 e to the negative 4th power will be 3.14. So pH is equal to 3.14 plus the log of conjugate base, which will be 0.002, 0.002 divided by our acid, which will be 0.008. So 3.14 plus the log of 0.002 over 0.008, which will give you pH of 2.54. C, calculate pH after adding 25 milliliters. So it's going to be the exact same thing. RBCA, HF plus OH minus, forming F minus plus H2O. This will be 0.01 as usual, and 25 milliliters so it's gonna be 0.2 molar of OH minus up here times 0.025 liters this time, which will give you 0.05. 0.005. If you subtract both sides by 0.05, you'll get 0 over here and 0.005 over here. If you plus 0.005 over here, you get 0.005. So when these two are equal, it shows you that this is half equivalence point. Half EQ point. So at half equal point, pH is equal to pKa. We found that pKa is equal to 3.14, so pH is going to be equal to 3.14. Do you calculate the pH after adding 40 milliliters? So RBCA one more time. Ca HF is plus OH minus, forming A minus plus H, no, not A minus, forming F minus plus H2O. It'll be 0.01 here, and this time is 40. So 0.2 molar of OH times 0.04 will be 0.008. So 0 over here, minus 0.008 on both sides is going to be 0 and 0.002, and plus 0.008 will be 0.008. So pH is equal to pK, which is 3.14, plus the log of, on the top is going to be conjugate base, which is 0.008, and on the bottom is going to be the acid, which is 0.002. So 3.14 plus the log of 0.008 on top divided by 0.002 on the bottom to give you 3.74 pH. Okay, let's calculate the pH at equivalence point. So RBCA. So let's use M1V1 to quickly find the equivalence point. M1V1 is 0.1 molar times 0.1 liters, right, in the beginning. 0.1 molar times 0.1 liter, yes. And then 0.2 molar of OH minus is equal to 0.2 molar of OH minus times X liters. So this is the equivalence point. So 0.1 times 0.1 divided by 0.2 will give you 0.05. So at 50 milliliters, or 0.05 liters, we're gonna have, that's gonna be an equivalence point. So it's gonna be HF again, HF plus OH minus, forming F minus plus H2O. So in this RBCA chart, we're gonna be using moles. So 0.1 molar of HF times 0.1 liters is gonna be 0.01 again, and our OH minus is gonna be 0.05 times 0.2, which is also gonna be 0.01. Now when you subtract these two together, it's gonna be 0, 0. It's going to be 0 over here plus 0.01, it will be 0.01 moles of F minus. Now, because there are none of these left, we cannot use our HH equation and to form a new reaction of our remaining stuff, which is our F minus. So when we add this to water, it's going to form HF plus OH minus. Now this is going to be a rice chart, so we're going to be using molar. And now, in order to convert this to molar, we're going to divide this by the new volume, which is 50 milliliters plus 100 milliliters, which would be 0.150 liters. So 0.01 moles of HF divided by 0.150 liters is going to give you 0.0667 molar. It'll be 0 minus X plus X plus X, 0.0667 minus X. XX. Since we're putting the OH minus this time, we're going to be using KB. So KB is equal to 1.0 e to the negative 14th divided by our Ka on the top, which is 7.2 times 10 to the negative 4th. This will be 1.39 times 10 to the negative 11th, which is equal to x squared divided by 0.0667 minus x. Delete the minus x because we assume the 5% rule, and 1.39 e to the negative 11th times 0.0667 takes the square root of that. We're going to get x is equal to 9.625 times 10 to the negative 7th. Because x is a concentration of OH minus, to find the pH, we're going to use the formula 14 plus log of x, and that will give us our pH. So 14 plus log of that number, which will give us 7.98. So that is our pH, 7.98. And over here, if you calculate the pH after the addition of 80, so our reaction again will be our BCA chart with HF plus OH minus forming F minus plus H2O. And HF will be 0. No, HF will be 0.01, same as both. And OH minus is 0.2 molar times 0.08 liters, which will give you 0.016. going to be 0, and this time we're going to minus a smaller number, which is HF now. So we will no longer have any acid left, and we'll have 0.006 plus 0.01 of 0.01. Now, because we have no more HF left, we cannot use the HH equation once again. But since we're now given with moles of OH, all we have to do is convert this to molar, which is now 0.180 liters. 0.006 moles divided by 0.180 will give you 0.0333 molar. Okay, so this is the concentration of OH minus. Okay, now that we have the concentration of OH minus, we can just do 14 plus the log of the concentration of OH minus, and that will give us our pH. So 14 plus the log of 0.0333 will give us a pH of 12.52. Okay, now we have to use all of them and graph it. So over here, our total is 80. So at the end bar is going to be 80, and this will be 0 over here. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. And our pH, we're going to come by 2s. So 1, 2, 3. Alright, so now let's start drawing. So we need to record off this. First we have when its initial is 2.07 and when 10 is 2.504. So initial is 2.07 and after that is 2.54. At 10 is 2.54. So about here and here. Let me draw them bigger. Alright. Next, when it's 25, it's 3.14 and 40 is 3.74. So over here it's going to be 3.14. Over here it's going to be 3.74. 3.74 about here. So now that we finished 40, equivalence, which is 50 milliliters, is 7.98, and finally is 12.52. So 7.98 and 12.52. 7.98, 7.98, and a 12.52 at 80. 12.52 is going to be this line. So this is how our titration curve is going to look like. We're going to have this and this. And this is our titration curve of, let's see, HF and NaOH. And that's it for this problem set. Thank you for watching.